Hello, everybody. Happy Wednesday. Welcome to your bonus lecture. So what I want to do is just quickly recap all of Chapter 9. I know I've spent a bunch of lectures on it. I want to just recap everything in one big 15-20 minute recap and then do a few example problems. And then tomorrow on Thursday, we're going to jump right into Chapter 10. So I started off Chapter 9 way back when, reviewing the scalar product or dot product. So keep in mind that when you're multiplying two vectors together, there's a couple different ways of doing it. Right now, the first thing we're looking at is the scalar product, and the end result is a scalar. No direction, just a number plus units. In Chapter 12, we'll look at what's called the cross product or vector product. But keep in mind, scalar product is just a number, can be positive, negative, or zero, but there's no direction associated with it. The dot product of two vectors, let me change this to green, is defined as the magnitude of one vector times the magnitude of the second vector times the cosine of the angle between them. Now, your book, I think, is using alpha. Some books use theta. The angle between A and B, the two vectors, is what we care about. Now, you can also show that if you're given x, y, and z components of the vectors, the dot product is also equal to ax bx plus ay by plus az bz. And the reason we care about the dot product is because work for a constant force is defined in terms of the dot product of the force dotted into displacement. After scalar product, I kind of went into just this big energy model overview. And an overview is this. We have a system. A system is just a collection of objects that you define. Within the system, there's this property called energy. And I kind of went through energy and work have this sort of circular definition. So work is a way of transferring energy from one object to another. And if an object has energy, it has the ability to do work, which means it has the ability to exert a force on an object over a displacement. So within a system, energy can be transformed from one form to another, but the total energy of the system doesn't change unless something outside the system is doing work on the system. So within a system, energy can be transformed from one form to another. Forms of energy that we have looked at a little bit. Potential energy. So I mentioned potential energy, but we're not going to see it until Chapter 10. We've got gravitational potential energy, an object in an elevated position. Once I drop it, that potential energy can get converted into kinetic and also elastic potential energy. But that's in Chapter 10, but I did mention it just as an overview and introduction to energy. The two forms that we're looking at in this chapter are kinetic energy, which is the energy of motion. It's 1/2 the mass times the speed squared, and thermal energy, which in essence is basically just heat. So within a system, energy can be transformed from kinetic energy to potential energy to heat, all different forms. But if no work is being done on the system, the total energy of that system remains constant. If the energy starts at 100 joules, it's always going to be 100 joules. On the other hand, if I do work on the system from something outside the system, so the environment, this is everything that's not the system. If the environment does work on the system, it will transfer energy either to the system or out of the system. If the environment does positive work, the energy of the system increases. If the environment does negative work, the energy of the system decreases. So work is just a way of transferring energy from one object to another. And initially, we were just looking at a single particle with a force acting on it. If that's the case, the only form of energy a single particle has is kinetic energy. And the work done on that particle will change the kinetic energy of that particle. Our big giant equation for energy is this. The work done by all external forces equals the change in energy of the system. Right now in Chapter 9, we're not looking at interactions of objects where there's a potential energy. So we're not looking at gravitational potential energy We're not looking at elastic potential energy. So the only forms of energy that we are looking at are kinetic energy and thermal energy. And in order to have thermal energy, you basically have to have a macroscopic sized object. So we're not looking at just single particles, but a crate, a box being pushed across the floor. Important thing about thermal energy, and I'll write this down in a second, is if you're going to include thermal energy in the energy of the system, everything that heats up must be part of the system. So if I push a crate across the floor and there's friction and the crate comes to rest, if I want to include thermal energy, then I have to include as my system the box and the floor, because both the box and the floor would be heating up. Okay, so again, here we got our system where energy within the system can be transformed between kinetic potential and thermal. Environment doing positive work increases the energy of the system. Environment doing negative work decreases the energy. Our big equation is the total work done, and this is by all external forces. This will equal the change in kinetic energy plus the change in thermal energy of the system. Kinetic energy is defined as 1/2 mv squared. M is the mass in kilograms. V is the speed in meters per second. Keep in mind, V is speed, not velocity. The units of all forms of energy are the joule, and a joule is equal to 1 Newton meter, which is the same thing as 1 kilogram meter squared per second squared. Thermal energy is generated anytime there is friction, and the equation for thermal energy, and this only tells us how much thermal energy is increasing. So the change in thermal energy equals the force of kinetic friction times the displacement over which it's acting. Keep in mind, your book is using S just as a generic variable. It could be X, it could be Y, it could be Z. I'm generally looking at stuff in the X direction. So our force of kinetic friction times delta X would give us how much thermal energy is increasing. Okay, and then in terms of the work done by any force can always be calculated as the integral of Fs ds. Or the way I've been doing it is work is equal to the area under the curve of Fx dx, which is the same thing as the integral from x initial to x final of Fx dx. That equation for work will always apply. However, if the force is constant, meaning it's not changing in magnitude, it's not changing in direction, then work is equal to the dot product of the force dotted into the displacement. Again, delta R is just our displacement. It could be in the x direction, could be in the y direction. But if the force is constant, then I take the dot product of the force dotted into the displacement. That will give me the work. Keep in mind that in this equation, work equals F dot delta R. That's equal to the magnitude of the force, which is always positive, the magnitude of the displacement, which is always positive, times the cosine of the angle between them. The angle between the two vectors is the only thing that determines whether the dot product is positive, negative, or 0. If the angle is between 0 and 90, that work done by that force is positive, it's adding energy. If the angle is 90 degrees, the work done by that force is 0. And if the angle's between 90 and 180, the work done by that force is negative. It's removing energy from the system. So a couple other things we looked at. A restoring force is a force that tends to bring an object back to equilibrium. Equilibrium is when the sum of the forces is 0. So for a spring, an ideal spring is one that can be stretched or compressed, and we define the equilibrium position to be when the spring is not stretched, not compressed. If I then were to pull the spring, and now I have stretched it some distance delta x. Hooke's law says the force that the spring exerts is always proportional to the displacement. But there's a minus sign. And let me just emphasize that. So this is the force of a spring, and I'm only looking at it in the x direction. That minus sign just indicates the direction of the force. You generally don't use it when you're drawing free body diagrams, and I'll do an example problem. But what this means is, in this case, here's my equilibrium position when the spring is not stretched or compressed. If I then stretch the spring a certain distance, this minus sign just indicates that the force the spring is exerting is in the opposite direction of the displacement. I displace the spring to the right, the force is to the left. A couple other things. One, since the force of a spring is not constant, right, as the spring gets more or less stretched or more or less compressed, the force it exerts changes, which means I can't use this equation for the dot product, F dot delta R, because the force is not constant. Because of that, you have to use this integral of fx dx, which once you plug in for the force, Hooke's law, what you end up getting is the work done by a spring equals -1/2. How do I want to write this? Let me write it with the minus sign out in front of everything. So -1/2 k times delta x final squared minus 1/2 k times delta x initial squared. So calculating the work done by a spring, you cannot use the dot product of F dot delta R because the force of a spring is not constant. Last thing we looked at was just power. Power gives the rate at which energy is being transformed or the rate at which work is being done. So power is just dE dt. And we measure power in watts. 1 watt is equal to 1 joule per second. I think that's it in terms of just the recap. So really big things in this chapter to know. Let's get the yellow. One, got to know the dot product, right? If I give you two vectors, you need to be able to take the dot product of those two vectors and know whether that dot product is going to be positive, negative, or zero. Definitely need to know the energy model. Energy within a system can be transformed from one form to another. If the environment does work on the system, then it changes the total energy of that system. Work is a way of transferring energy. I can always use this equation for work, the integral of fx dx. But if the work is done by a force which is constant, then I can do the dot product of F dot delta R. The work done on a system results in the total energy of the system changing. And right now, we're only looking at kinetic energy and thermal energy. Kinetic energy is energy of motion. The equation is 1/2 mv squared, where v is the speed. Thermal energy is basically heat. And the equation for how much thermal energy increases is the force of kinetic friction times the displacement. And yeah, Hooke's law basically says the force a spring exerts is equal to some constant called the spring constant times the displacement. And the force is always in the opposite direction of the displacement. So the equation is -k times delta x if we're talking about in the x direction. And the work done by a spring, I cannot use the dot product because the force is not constant. And energy. Power and energy are related in that power tells us how quickly energy is being transformed. So a 100-watt light bulb, a watt is a joule per second, means every second 100 watts of energy are being transformed from one form to another. In terms of a light bulb, it's from electrical potential energy into heat and light. Okay, so let's just do 3 example problems and then we are done chapter 9. Tomorrow I'm going to go into chapter 10, and you'll see I'll cover the whole chapter in a day and then just spend a couple days doing example problems. So first, let's take a look at example problem 9.10. It says this. The cable of a crane is lifting a 750 kilogram girder. A girder is just a big old girder, big old whatever. The girder increases its speed from 0.25 meters per second to 0.75 meters per second in a distance of 3.5 meters. How much work is done by gravity? How much work is done by tension? So you've got this girder, like a big old rod or something. It's initially moving at 0.25 meters per second and then ends up going, after moving a distance of 3.5 meters up, it's now moving at a speed of 0.75 meters per second. So if I were to draw a free body diagram, I basically just have two forces. I have tension and I have mg. So anytime we're dealing with these problems, first thing you want to do is really define your system. In this case, my system is just going to be the girder. In which case, thinking about the external forces, tension and gravity are now both external forces. So I can figure out how much the total energy changes if I know the total work done by all external forces. So first thing I want to know is, what is the work done by gravity? And oh, I guess I forgot to put that on this important concepts up here. So let me just throw that up here real quick. Basic work done. That's funny they don't have that on the review. So anyway, big thing here. Where's my work done by gravity is equal to negative mg delta y. The minus sign comes about because as an object moves upwards, when delta y is positive, gravity acts straight down, so the angle between the displacement and the force is 180 degrees. So this is definitely another important equation for this chapter that I forgot to include up there. Okay, back to the example problem. Part A, they just want to know what is the work done by gravity. Very simple. Work done by gravity is negative mg times delta y. So in this case, the mass is 750 kilograms, g, 9.8 meters per second squared. Never negative 9.8, never, never, never! And delta y, it increased in elevation by 3 meters. If you calculate the work done by gravity, what you'll get is it's negative 25725 joules. I'm just keeping a bunch of significant figures until the end. So part A, very simple, work done by gravity, always going to be true, negative mg delta y. Part B, we want to know what is the work done by tension. So one, here's a good little check for you to do as a review. I could figure out the work done by tension by figuring out the force of tension using Newton's second law, the sum of the forces in the y direction equals may, and I could calculate what the acceleration is because I know the initial velocity, I know the final velocity, I know the displacement over which it acted. I could calculate the acceleration. But we're going to do this using energy. So I know the work done by all external forces equals the change in energy of the system. And again, we're just looking at the change in kinetic energy plus the change in thermal energy. If there's no friction, no air resistance, no thermal energy is going to be generated, don't need to consider that in this case. So only looking at the change in kinetic energy. And the work done is the work done by all external forces, which in this case is the work done by tension and the work done by gravity. So the work done by external forces is the work done by tension plus the work done by gravity, which we've already calculated, and that equals the change in kinetic energy. So 1/2 mvf squared minus 1/2 mv initial squared. Well, we already have the work done by gravity, so we can just solve for the work done by tension, and we don't actually need to calculate the force of tension. So the work done by tension is just going to be equal to 1/2 m, and I'm just going to factor that out, so times Vf squared minus V initial squared minus the work done by gravity. Well, we've got the mass, we've got the initial speed, we've got the final speed, we've got the work done by gravity. Let me just skip the step of writing out all the numbers, but once you plug in the mass, the final speed, the initial speed, and the work done by gravity, what you'll find is that the work done by tension is 2.59 times 10 to the 4 joules. So that is our answer to part B. So anytime you want the work done by gravity, it's always negative mg delta y. In this case, to get the work done by tension, we just take into account the fact that the work done by all external forces equals the change in energy of the system, which in this case just results in the kinetic energy changing, and there were only two forces doing work, tension and gravity. Okay, moving on. Problem 933, and I'm going to do this two different ways just to show you that depending upon how you define the system, one case there'll be thermal energy and the other case there won't. So problem 933, a baggage handler throws a 15-kilogram suitcase along the floor of an airplane luggage compartment with a speed of 1.2 meters per second. The suitcase slides 2 meters before stopping. Use work and energy to find the suitcase's coefficient of kinetic friction on the floor. All right, so here's the situation. I've got a suitcase that's moving at 1.2 meters per second, and let's just assume it's moving to the right. There is friction, and because of friction, after sliding 2 meters, this thing comes to rest. And we want to know what is the coefficient of kinetic friction. So again, our work energy principle says that the total work done by all external forces equals the change in kinetic energy plus the change in thermal energy. But an important piece is that if you're going to use thermal energy, everything that heats up must be part of the system. So to use delta E thermal, everything whose temperature increases must be included in the system. So what I'm going to do is I'm going to look at this actually two different ways. One way, I'm going to include the floor as part of the system, in which case we can include thermal energy. Second way, I'm not going to include the floor, which means kinetic friction will be an external force doing work. So let's do it the first way, one. And let's say that I'm defining my system as just the suitcase. So one, if I draw a Freebody diagram on this suitcase, I've got the normal force, which is really the force that the floor is exerting upwards on the suitcase. I've got gravity, which is the force of the earth pulling down on the suitcase. And I've got kinetic friction acting in the opposite direction of motion. Now, if I define my suitcase as the system, the normal force is an external force, gravity is an external force, kinetic friction is an external force, which means my external forces are all the forces. I've got the normal force, I've got kinetic friction, and I've got gravity. So when I do the work done by external forces equals the change in energy of the system I'm only considering the change in kinetic energy because the floor is not part of the system and it also heats up. So what I have is the work done by the normal force plus the work done by kinetic friction plus the work done by gravity equals 1/2 mv final squared minus 1/2 mv initial squared. Quick question for you before I continue on with this problem. I've got 5 different terms, 3 work terms, 2 kinetic energy terms. How many of those terms drop out? Do, 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 do. Okay, the answer is 3. Which 3? Well, this suitcase ends up at rest, which means its final speed is 0, which means its final kinetic energy is 0. What other 2 are 0? Well, remember that this object is getting displaced delta x to the right. So when I go to calculate the work done by the normal force, the angle I would use is 90 degrees, which means the work done by the normal force is 0. When I go and I calculate the work done by gravity, again, I'm going to get 0 because the angle between force of gravity and the displacement is 90 degrees. And keep in mind, I can use this work equals F dot delta R, or in this case, delta X, because the normal force is constant, the force of gravity is constant. So the work done by the normal force is 0, the work done by gravity is 0, and what I get is the work done by friction equals negative 1/2 mv initial squared. So the work done by any force that's constant is the magnitude of the force, so in this case the force of kinetic friction, times the displacement, delta x, times the cosine of the angle between the two, which in this case is 180 degrees because this object is getting displaced to the right, force of kinetic friction is to the left. So this equals negative 1/2 mv initial squared. And let me just draw the Freebody diagram again. I've got normal force, mg, force of kinetic friction. We know the force of kinetic friction is mu k times the normal force. And in this case, when the only 2 forces acting vertically are the normal force and gravity, and it's not accelerating, I know the normal force is just going to equal the weight mg. So my force of kinetic friction is mu k mg. So what I get is coefficient of kinetic friction times mg times delta x equals negative 1/2 mv initial squared. And then once I solve for the coefficient of kinetic friction, what I'm going to get is what? V initial squared. Oh, one thing I forgot here. This cosine 180 is a negative 1. Let's just put that out here. So again, this minus sign came from the cosine of 180. So this minus sign cancels out with this minus sign. Solving for the coefficient of kinetic friction, what I get is mu k equals v initial squared over 2 times g times delta x. And again, I'm going to skip the step of just writing out the numbers. My initial speed is 1.2 meters per second. My delta x is 2 meters. The mass drops out. I know g is 9.8. Put all these in, and what you're going to get is the coefficient of kinetic friction is, let's look it up, and I'm going to assume the book answer is right, which is always an interesting assumption, but 0.037. So in this part of the problem, I defined my system as just the suitcase, which means the normal force, gravity, and kinetic friction were all external forces, and I can't consider thermal energy because I'm not including the floor as part of the system. So let's do this problem again, but now let's include as our system the suitcase plus the floor, or let's say plus the surface. Again, it's not the entire Earth pulling down on the suitcase that I'm including as part of the system. It's just the surface that the suitcase is on. Now, how does that change things? Well, now the normal force and kinetic friction are part of the system. Well, I shouldn't say, let me say, they're not part of the system, but these are now internal forces. Why are these internal forces? Well, the answer is because the normal force is just the floor pushing up on the suitcase. So that's two things in the system exerting forces on each other. Kinetic friction is just the floor retarding the motion of the suitcase. Again, that force is part of the system. So now my only external force is the force of gravity. So now when I look at the sum of the work done by all external forces equals the change in energy of the system, now I can include thermal energy because I've included the floor as part of the system. Now the only work that's done by external forces is the work done by gravity. Again, change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. And my thermal energy is the force of kinetic friction times the displacement. Now, just like previously, the work done by gravity is 0 because gravity's pulling straight down, the box is being displaced to the right. So this work done by gravity is 0. And again, this thing ends at rest, so its final speed is 0. What I get is 0 equals negative 1/2 mv initial squared plus the force of kinetic friction times delta x. And if I just move the force of kinetic friction times delta x over to the other side, what I basically have is negative mu k mg, where this is the force of kinetic friction, times delta x equals negative 1/2 mv initial squared. And that's exactly what I have up here. I get the exact same answer. So in one case, I only included the system as the suitcase. All forces were external forces. And I couldn't include thermal energy because I didn't have the floor as part of the system. Now, second case, I've included as a system the suitcase and the floor or the surface, which means the normal force is now an internal force, and so is kinetic friction. But now I can include thermal energy. All right, very last one. Problem 9.28. A 60-kilogram student is standing atop a spring in an elevator as it accelerates upwards at 3 meters per second squared. The spring constant is 2,500 newtons per meter. By how much is the spring compressed? So, we just kind of draw this poorly. You have somebody in an elevator and they're on a spring. In essence, they could be standing on a scale because all a scale is, just so you know what happens when you stand on a scale, you're compressing a spring. By knowing how far the spring is compressed, you know the force the spring exerts, which is also going to equal the force of gravity on you. So actually, when you step on a scale, what you're really measuring is the force the spring is exerting upwards on you, which is equal to the force that gravity is pulling down on you with, which is equal to your weight. So you're actually not getting your mass at all. You're getting your weight, which hopefully you remember that. Okay, so if I draw a free body diagram, I have two forces. I've got the force of the spring straight up, and I've got the force of gravity, mg, straight down. And this guy is accelerating upwards at 3 meters per second squared. Now, one thing about this in terms of free body diagram, let me just redraw this. The force that the spring is exerting upwards, I'm going to call K times delta Y, where delta Y is how much the spring is compressed, or in this case compressed, and mg. I am not using the minus sign in drawing a free body diagram because the minus sign just indicates that the force is in the opposite direction of the displacement. So before the person steps on the scale, let's say this is where the spring normally is. Then they step on the scale and it compresses the spring some distance delta y downwards. So the spring is compressed downwards, which means the force the spring exerts is straight up. That's what the minus sign is indicating in the force of a spring is negative k times delta x or delta y or whatever. This minus sign is telling us that whatever way the spring is compressed or stretched, the force it exerts is in the opposite direction. So here the spring was compressed down, it's exerting a force up. So now all I do is apply Newton's second law. Sum of the forces in the y direction equals MAY. Forces in the y direction are force of the spring, K delta y straight up, minus the force of gravity, mg straight down, equals MAY. What are we looking for here? How much is the spring compressed? So I'm solving for delta y. So my delta y is going to be m times ay plus g divided by the spring constant. We have the mass is 60 kilograms. We've got ay is 3 meters per second squared. G is 9.8. I've got K is 2,500 newtons per meter. Plug everything in, and delta y ends up being 0.31 meters. All right, that was it. I feel like that was a pretty thorough recap of Chapter 9. That's everything you need to know to do the homework and to do the quiz. So stay tuned tomorrow, Thursday, for introducing Chapter 10, all about conservation of energy. I'm going to simplify it greatly and pretty much cover everything you need to know, hopefully, in one lecture. All right, that is it. Happy Wednesday.